Thank you. So first of all, I have to declare that I previously was employed by Siemens Healthcare and that I still get royalties from the company. Okay, so I guess everybody attending this conference will agree that MRI is a pretty amazing imaging technique. It's free of ionizing radiation, and it allows us to measure a quite big number of different tissue properties and functional parameters. But unfortunately, MRI also has two major limitations. First of all, the data acquisition itself is relatively slow if we compare it, for instance, to ultrasound. And second, it's very sensitive to motion. And these limitations are, of course, a particular problem for cardiac imaging, because here we have two concurrent types of motion. We have very fast cardiac motion, and in parallel to that, we have slower but potentially very irregular respiratory motion. And so to image the beating heart with MRI, we need to use some tricks, and this is the conventional strategy. So to handle the cardiac motion, we are synchronizing the data acquisition with an ECG signal, so that we get data with consistent cardiac phase. And to handle the respiratory motion, the data is acquired while the patient is performing a breath hold. And so using these two tricks, it's possible to get very nice image quality. But unfortunately, in clinical practice, this does not always work that well. First of all, it can take quite a long time to properly set up the ECG, and then sometimes the ECG signal is not stable, or the patient has arrhythmia, and in these cases, you can get image quality like this. And then what also sometimes happens is that the patient is not able to perform a breath hold, and in this case you get image quality like this. And also the overall examination workflow is quite complex. There are many different protocols, and there are also a lot of potential pitfalls where technicians can make mistakes. And as a result of these difficulties, the clinical utilization of cardiac MRI is still relatively low compared to other MRI applications. And just to give a number here at our center, the volume of cardiac MRI scans makes about 1.4% of the total MRI volume. So what I want to do in this talk today is give an overview of a couple of new recent technical developments in MRI research that potentially might help to solve these issues and that might help to make cardiac MRI exams more reliable and also more time efficient. And this is the list of topics that I want to discuss, and it's just an overview, so I won't go into any details. And this list is also not complete, but the reason why I picked these topics is that all these concepts help to improve cardiac MRI scans individually, but they can also be combined in a modular fashion, and if we do that, and if we combine all these techniques, then we get an approach which I believe could be a future direction for cardiac MRI. And I will conclude with saying a couple of words about this combined approach. Okay, let's start by taking a look at why is MRI actually so sensitive to motion. And this really goes down to the phase encoding principle, which is used by almost all clinical MRI sequences. So in the phase encoding principle, the spins need to have a different phase, need to have a constant phase difference between the different K-space lines that we acquire. And unfortunately, it's a mathematical property of the Fourier transformation that if we shift the object in image space, then we get a phase modulation in frequency space. And this means that if we have motion in the image space, then we get spurious phase perturbations in K-space. And you can think of this, and these spurious phase perturbations, they disturb our phase encoding principle or phase encoding scheme. And you can think of this as jiggling around the K-space lines a little bit. And as a result of that, we get local violations of the Nyquist limit. And therefore we are getting ghosting artifacts, which are basically shifted object copies that propagate along the phase encoding direction. So this motion sensitivity really is a result of this row-by-row acquisition of K-space. And therefore we can improve the situation by using a different sampling geometry. And one option is to use a radial acquisition of K-space, where we are sampling K-space along these overlapping spokes. And this idea is actually an old hat. This has already been described by Paul Lauterbur in 1973. However, after the invention of phase encoding, radial sampling has not been used very often anymore. And in particular, it has never been really used for clinical applications. And the reason is that radial sampling has higher technical requirements, including a more complicated image reconstruction, and we also need very precise timing of the gradient fields. And so these higher technical requirements made it quite difficult to implement radial sampling robustly on the early MRI systems. But today we now have better MRI systems, and so using modern MRI systems, radial MRI sequences now work sufficiently reliable. And so nowadays it's actually possible to use these radial sequences for routine imaging. And if we do that, and if we switch our acquisition scheme to such a radial scheme, we are automatically getting a significantly higher robustness to motion. And you can see this in these abdominal scans here. These two abdominal scans have been acquired during free breathing using exactly the same sequence and the same sequence parameters. The only difference was that on the left side, phase encoding has been used. And here you can see all these ghosting artifacts as a result of the respiratory motion. And on the right side, radial sampling has been used, and here we still get pretty good image quality, although the patient was breathing. And this higher robustness is just a consequence of this different sampling geometry, because in the radial case, we have a significant oversampling of the K-space center, which inherently has a data averaging effect, and we have different readout directions. So there's no phase-encoded axis where all spatial information is just encoded using the phase, and therefore it's impossible that we get these ghosting artifacts. And so simply by switching the sampling geometry to radial sampling, we are getting higher motion robustness, and it becomes possible to acquire data during free breathing. Now the next question is, how fast can we get with such a radial acquisition? And the acquisition speed per image is simply given by the number of K-space lines that we acquire multiplied by the repetition time. And if we want to have a fully sampled data set, then the number of spokes that we need is pi over 2 times the base resolution, which means we're actually a little slower than with a phase-encoded scan. Now, if you want to get faster, then the only option that we have is to reduce the number of K-space lines. And if we do that, and if we reduce the number of spokes, then we're undersampling the data, and this means we will get undersampling artifacts. And in the radial case, these are these so-called streaking artifacts, which you can see here in these simulations. So the fewer spokes we acquire, the stronger are these streaking artifacts. But what's interesting about these streak artifacts is that they have a very distinctive visual appearance. And they look like a texture which is added to the object, while the underlying spatial resolution is largely preserved. And therefore a certain amount of streaking artifacts can often be tolerated. And so by selecting the number of spokes, we can make a certain trade-off between scan time and the amount of artifacts that we are willing to accept. Now the next question is, in which order should we acquire these radial spokes? And here the Philips group in Hamburg had a very smart idea, which is called the golden angle ordering scheme. And this works as follows. We start at an angle of 0 degree. And then for the next spoke, we always increase the angle by 111.25 degrees, which is called the golden angle. And you can see the scheme in this animation here. And there are basically 3 things you can see here. First of all, if we follow the scheme, then we will never sample the same spoke twice. So we are always sampling a slightly different angle. Then the next spoke that we acquire will always fill the largest gap of the previously acquired spokes. And third, at any time point of the acquisition, we always have a quite uniform coverage of K-space. So there are no big gaps in K-space. And these properties are independent from the actual number of spokes that we have. So by following this simple scheme, we are inherently getting an optimal distribution for any number of spokes. And this enables us also to calculate images from an arbitrary number of spokes. So we don't have to think about how many spokes we want to acquire. We can always reconstruct an image. And this allows us to do the following thing. So instead of pre-selecting a temporal resolution and then running the same scan over and over again, which is what you conventionally do, we can just do one continuous acquisition using this radial golden angle scheme. And then in the reconstruction, we can take the continuously acquired data and group the spokes from this continuous scan into different image frames. And in this way, we can calculate different images. And this means that we can retrospectively decide what temporal resolution we want to reconstruct, and we can also decide which time points we want to reconstruct. And it's also possible to do different reconstructions of the same data set. So if we select a wide reconstruction window, then we have many spokes for each frame, which means we will get good image quality, but of course we have a pretty long temporal footprint. If we select a narrow window, then we only have few spokes, which means we are undersampling the data, so we will get streaking artifacts, but here we now have a better temporal fidelity. So by using this continuous acquisition with this golden angle scheme, we can make the trade-off actually during the image reconstruction between high image quality and getting good temporal fidelity. And on the next slide, you can finally see some cardiac scans. So these are radial scans which have been acquired using a radial balanced SSFP sequence without any ECG gating and during free breathing. These movies have been provided by Ralf Bauer from University Hospital in Frankfurt. And on the left side, in this movie on the left side, 125 spokes have been combined into each frame, which means we are getting a temporal resolution of about 300 milliseconds here. And in the middle, only 15 spokes have been used per frame. And at first glance, this doesn't look too bad. This is now free breathing without ECG synchronization. But if you look closely, then here in this left case, you can see that the wall motion is not sharp. So we have blurry wall motion, and this is simply a result because we have a pretty long temporal footprint. Now in the middle, the situation is better, but in this case we do see some streaking artifacts, and also the contrast to noise ratio is not that great anymore, and this is because here we have undersampled data. So this is kind of this trade-off between getting good image quality and getting good temporal fidelity. Now, is this still good enough for a quantitative diagnostic analysis of these images? And the group did a study on that, and it turned out you can actually use these images for a diagnostic analysis if the heart rate is not too high, but it's definitely preferable to get faster imaging speed. Now, these scans were done at maximum acquisition speed, so at maximum gradient speed. So how can we get any faster than this? And this is possible by using a reconstruction trick. So if you continue to undersample the data to get faster, then we get stronger and stronger streak artifacts. And so in the simulation here, only 5 spokes have been used per image. And in this case, we are very fast, but you can basically only see streaking artifacts in this image or in these images. Now, what's quite interesting, what happens if I take these images and play these images at a faster speed. So these are exactly the same images, and if you look at this for a moment, you can again see that this is a Shep-Logan phantom, and you can even see certain details of the Shep-Logan phantom. So why is that the case? It is the case because by playing these images faster, our brain is able to understand that there's correlation between sequential images, and it's able to identify these flickering streaks as artifacts. And so this is a trick which we can also use for our image reconstruction. So the idea is that we make use of the fact that we know that there's correlation between sequential images, and that we do know that the true solution does not flicker. So flickering is an artifact. And now to incorporate this into our image reconstruction, we have to perform an iterative image reconstruction. And I'm not going into any details here because this is a whole field. But the basic idea is that we use a different reconstruction scheme where we start with a black image. Then we are running an iterative optimization procedure. And during each iteration, we are taking our image estimate and we are comparing it to our undersampled measured data. And then we are updating the image estimate. And in addition to that, we can also test and enforce that our image estimate complies with prior knowledge that we have about the solution. And in this case, the prior knowledge that we have is that we know that the true solution does not flicker. And so by running this iterative reconstruction, we can then suppress these flickering, streaking artifacts and can recover the undersampled images also from highly incomplete data. And this is again not a cardiac example, but this example nicely shows how effectively this can work. So on top, this is kind of our normal standard reconstruction where you see all these flickering, streaking artifacts. And down here, this is now this iterative reconstruction where these streaking artifacts have been removed. And on the next slide, you can see some cardiac scans which have been reconstructed using this strategy. These movies are from the group of Jens Frahm at Max Planck Institute Göttingen. They are using a radial flash sequence with a nonlinear inversion reconstruction algorithm, which additionally also incorporates parallel imaging. And so by performing this temporally constrained reconstruction of this radial data, it's then possible to reconstruct images from only 17 spokes per frame, which gives you a temporal resolution of 33 milliseconds. And as you can see in this case, we now have sharp wall motion, and we do not see streaking artifacts, although the data is significantly undersampled. So by performing an iterative reconstruction of the radial data, we are actually becoming fast enough to image the heart without ECG synchronization. And on the next slide, you can see another example on the left side. And in this case, they were really pushing the limits. In this case, only 5 spokes per image have been used. And here we are getting a temporal resolution of 10 milliseconds. And this is now really real-time imaging. So it's also possible to change the slice orientation during the examination, or it's possible to play out tagging pulses during the scan, as shown here on the right side. Now, if we perform these scans during free breathing, we will of course see that the position of the heart is changing as a result of the respiration, and this can be a problem for certain applications, but fortunately there's also a solution for that. So if we're performing a radial acquisition, then we have a continuous acquisition of the K-space center information because all the spokes go through the center of K-space. And therefore, a radial sequence is also inherently capturing information about the respiration that occurred during the examination. And so if the patient is breathing, the amount of dark lung tissue is changing, as you can see in this movie here, and therefore also the total image intensity of the image will change, which is simply the sum over all pixel values. And this total image intensity is represented at the K-space center. So if we take our radial spokes and plot the k-space value whenever we go through the center of k-space, and if we plot that along time, then we get such a respiration curve. And this respiration curve tells us when and how the patient was breathing during the examination. And we are getting this information for free from the imaging data. And it's not just possible to generate such a respiration curve, it's actually possible to use that respiration curve to actively compensate for motion, and this is a concept known as self-navigation. And it's even possible to go one step further. It's possible to detect both respiratory motion as well as cardiac motion, both from the imaging data. And it's possible to distinguish between cardiac motion and respiratory motion by looking at the signal from different coil elements. So if you want to get the respiratory motion information, we are taking a look at the k-space signal that we get from a coil element that's located above the liver. So signal changes that we see at the k-space center in this coil, this is mainly caused by respiratory motion. So in this way we get this respiration curve. And to get the cardiac curve, we are taking a coil element which is located above the heart. So signal changes that we see in this coil, these changes are mainly caused by the contraction of the heart. And so by looking at these different coil elements, we can get these two different motion curves for respiratory motion and cardiac motion. And these curves are usually noisy, so we have to apply some clever filtering. And then we can take these curves, and we can then bin these curves into different motion states. So we can bin the respiratory curve into different respiration states, ranging from inspiration to expiration. And we can bin the cardiac curve into different cardiac states, ranging from diastolic phase to systolic phase. And then we can take our time series of acquired spokes and we can assign a motion state to each acquired spoke. So for each acquired spoke, we now know what the respiratory position was and what the cardiac state was. And once we have done that, we can then take our time series of acquired spokes and we can sort these spokes according to the motion state. So we can take these spokes and throw them into these bins depending on their motion state. And in this way, we get this two-dimensional array of different parametric frames. And these parametric frames correspond to different combinations of respiratory and cardiac states. So if we look into this dimension of our two-dimensional array, then we have data for different respiratory positions. And if we look in this dimension of this array, we have data for different cardiac positions. And of course, the data that we have for these different parametric frames is usually highly undersampled, so we will see streaking artifacts in these images. But of course, there's again a lot of correlation between these different parametric frames. And therefore, we can again use our iterative reconstruction idea. But in this case, the idea is to not apply iterative reconstruction along the time domain. In this case, we want to apply it along these newly created parametric dimensions. So in this case, we want to suppress flickering, streaking artifacts along these newly created respiratory dimension and this newly created cardiac dimension. And by doing this in this way, it's possible to eliminate the streaking artifacts in these different parametric frames, and it's possible to recover all these different parametric frames. And this is what's called an extra-dimensional reconstruction. And on the next slide, you can see an example that illustrates what the value of this extra-dimensional reconstruction is. This example has been provided by Li Feng and Ricardo Otazo from NYU. And this is again a radial free breathing scan. And on the left side, you can see a normal conventional iterative reconstruction where we are penalizing these flickering, streaking artifacts along the time domain. So this is actually not too bad, but here we still see some residual artifacts, and you can see that the patient is breathing. And now in the middle, you can see this extra-dimensional reconstruction. And because in this case, we now have these newly created dimensions, we have a cardiac dimension and we have a respiratory dimension. And therefore, we can now play back the cardiac motion at a fixed respiratory position. And in this way, we can virtually freeze the cardiac motion, the respiratory motion. So we can just let the patient breathe normally, and then when we want to look at the images, we can kind of stop the respiratory motion and we get images with a fixed respiratory position. And this is the advantage of this extra-dimensional reconstruction. And of course, this also works for patients with severe arrhythmia, because in this case, we are extracting the cardiac information from the data itself instead of using an external ECG signal and instead of relying on arrhythmia detection. And of course, we can also turn things around, and we can not only freeze the respiratory motion, but we can also freeze the cardiac motion, and we can look at how the heart is deformed when the patient is breathing. And this is shown in this video, which is again from Li Feng. And so in these different images, you can see different cardiac phases. And in the movie, you can see how the heart is deformed in this cardiac phase when the patient is breathing. And especially in the diastolic phase, you can now see this movement of the intraventricular septum, which becomes possible during the respiration. And this is an effect which we can now look at using such an extra-dimensional reconstruction. So this might actually even add diagnostic value. Okay, everything we discussed so far was only for a single slice. Can you also do this for a volumetric acquisition? And the answer is yes, because if we use such a self-navigation mechanism, it's not necessary anymore to acquire all data as fast as possible, and it becomes feasible to also use such a radial 3D Couche-Ball trajectory. And with such a Couche-Ball trajectory, all the spokes still go through the center of K-space, and therefore we also get a self-navigation signal for each acquired spoke. Now, if we use such a 3D Couche-Ball trajectory, we now have two different radial angles which we have to select. We have a polar angle and an azimuthal angle. And there are many different ways how to select these angles and how to select the acquisition order. One option is to use the spiral phyllotaxis scheme, which has been described by Davide Piccini from Siemens. And in this scheme, the sphere is divided into such short segments, which are then rotated by the golden angle, so that this scheme gives you very similar imaging properties as the original golden angle ordering scheme. So it's kind of a 3D extension of golden angle ordering. And the big advantage of using a volumetric acquisition is that we now have isotropic spatial resolution. And this means that we can retrospectively generate any desired image orientation from this 3D scan. So we do not have to think about what imaging slices we need or imaging planes we need. And this means that all slice planning steps are eliminated that are conventionally needed during the examination. And of course, this 3D approach can be combined with all other concepts that we discuss. And if we do that and throw in iterative reconstruction and throw in self-navigation, then it becomes possible to use a completely new examination workflow. So instead of using the current sequential examination workflow, where we are first acquiring a number of localizers, and then we are sequentially scanning in different orientations, and of course during each of these scans the patient has to perform a breath hold. So instead of doing that, we can just do one continuous acquisition using this radial 3D sequence while the patient is breathing normally and without ECG use. And then later, if we want to look at the images, we can take this Couche-Ball of radial data, run our iterative reconstruction, run the self-navigation, and we can then basically generate any desired image orientation and any desired motion state from this data set. And we can not only look at myocardial function in different orientations. Since we have an isotropic resolution, we can also look at the aorta, both in a static view where we are freezing the cardiac motion, as well as in a functional view where we are playbacking the cardiac motion. And we can also look at the aortic root, we can look at pulmonary arteries, and it's even possible to look at coronary arteries, both again in a static view where we are stopping the cardiac motion, as well as in a functional view where we are playing the cardiac motion. And this is again shown in this slice here, in this figure here. All these images are first results from a collaboration between the groups of Matthias Stuber in Lausanne and Ricardo Ottauser at NYU. And this demonstrates that it's actually possible to get both functional information as well as morphological information all from one single acquisition, during which the patient can breathe normally and without using an ECG. And I think that this really, this of course results in a significant simplification of the examination workflow. We only need one scan instead of all these different scans. And I think that this has a lot of potential for simplifying cardiac MRI scans and also to make cardiac MRI scans more reliable and more time efficient. Okay, to quickly summarize what we discussed, I think the next generation of cardiac MRI techniques should use a non-Cartesian acquisition scheme, such as radial sampling, which gives an overall higher robustness to motion. It should use the golden angle ordering acquisition scheme, which allows us to do continuous data acquisition with a flexible temporal resolution. It should use iterative reconstruction, which gives us the speed needed for non-gated examinations. It should use self-navigation, which allows us to retrospectively freeze cardiac motion, and it should use a volumetric acquisition, which eliminates the need for localizer scans and scan planning. And if we combine all of this, then it will be possible to do point-and-shoot cardiac examinations, as just discussed, without the need for breath holding, without the need for ECG synchronization, and without the need for detailed scan planning, and we will have a much more simple examination workflow. And at the moment, this is of course still a vision, and there's still a lot of work that needs to be done. But all components that we discussed have been demonstrated on existing clinical MRI systems. So the hardware is able to do this, and it's now more or less just a question of software engineering to put this approach together. And so maybe it will actually not take that long until such a point-and-shoot cardiac approach will become clinically available. And with that, I want to thank the people that provided me with material for this talk, and I want to thank you for listening.